Stefan, could you let me know when Lydia connects? Because apparently you can't switch screens once you put on the presentation. Yeah. Yeah, I think, oh, sorry, I did not, I forgot to press send. The draft is there and just, I thought I would schedule it to. Sorry. No, actually, I'm going to share my screen as soon as. No, no, sir, it's. I, yeah. Okay.
Does that work? Can you hear me? Not sure.
I think.
Doesn't sound like it works, does it?
Antoine? Le micro.
I have no mic. I don't think. Yep, does it work? Yep, okay. Good afternoon, everybody. So I have the honor to be the president of the jury of the thesis of Sagar Pal. I will present the member of the jury, so starting with the people who are connected remotely. So we have Lydia Boruiba, who is an associate professor at MIT. We have Professor Heinz Pitsch from the University of Aachen. We have Jean-Luc Estivales, who is a research scientist at Onera in Toulouse. We have Marika Pelanti, who is a maître de conférence at ENSTA Paris. We have the two PhD advisors, so Daniel Fuster from here d'Alembert, and Stéphane Zaleski, also from here, professor at Sorbonne Université, and myself, I'm Stéphane Popinet, and I'm a TNRS researcher here at Sorbonne also. So we will listen to you for 45 minutes.
Okay.
And then we'll ask questions afterwards.
All right.
You can start.
Can I just verify if the audio is working with? Stefan, can you turn off your volume, please? So, Professor Heinz Pitsch, Professor Lydia, can you hear me? Jean-Luc? All of you can. Okay, okay. So if at any point of the time you have any difficulty with the audio, just let me know. All right? Okay. All right. So good afternoon, everybody. First of all, I would like to thank you very much for taking out the time to attend my PhD defense. And so today I shall be presenting some of the key highlights of my work that I have carried out at the Institute with under the supervision of Daniel Fuster and Stefan Zaleski. So starting off, I present a brief outline on the topics that we shall be covering today. First of all, in terms of the introduction, I will be briefly presenting some of the basics of liquid-gas interfacial flows, and then we shall move on to part A, then part B, and finally with the conclusion and perspectives. So in part A, what you have here is we basically design and develop numerical methods so that we can tackle some particular challenges when it comes to dealing with liquid-gas interfacial flows. And in part B, we shall use a different set of methods to ask or study something more physical in terms of the fragmentation. So starting off, one can ask the question, okay, what is a good example of a liquid-gas interfacial flows? Well, they are ubiquitous in nature, as you can see with this simple schematic to start off. Over here you have one fluid which is surrounded by a different fluid. The inner fluid, you can, if it's a gas, it's a bubble. If it's a liquid, it's a drop. And they are separated by an interface which is characterized by a surface tension sigma. And you might, so one of these drops and bubbles are amongst the key elements of surface tension driven flows. And they are hugely relevant in the dynamics of ocean-atmosphere interface, especially the mass transfer and heat transfer, in the context of mixing and separation in metallurgical processes, especially in the mixing of air and fuel for anything that involves combustion. And more recently, which is of particular relevance these days, is pathogen transmission in the form of droplets of different sizes. So moving on. So what are the key challenges that we face over here? So if you look at this nice photograph, it captures perfectly a breaking wave, and uncannily, it gives us a good idea of all the challenges we have related to liquid gas multiphase flows. So over here, you can see at the topmost edge, you have these extremely fine droplets, and on the other hand, you have this huge wave. So you have incredible scale separation in terms of the length scale. So approximately 10 to the power 5 in each direction. So imagine if you're trying to do a 3D simulation, you're going to need around, I don't know, 100 billion points to just resolve something meaningful. On the other hand, you have, of course, you have your nonlinear interactions, which entails the transfer of energy across different length scales and going into the regime of turbulence and all the associated complications. And finally, you have, on top of the already complicated interactions between inertia and viscosity, you also have the third member, which is the capillary forces. And finally, to top it off, you have the mathematical transport of discontinuities, which appear in the form of the large density and viscosity contrasts that occur across the interface. So what are the numerical platforms that we use? The numerical platforms are basically Paris Simulator and Basilisk. Both of them have been primarily developed by people, by researchers at our lab, and also more or less an international set of collaborators. Some of the key takeaways from here are both of these methods employ state-of-the-art geometrical volume of fluid methods, and as well as state-of-the-art implementation of surface tension, which are some of the most important aspects when it comes to trying to simulate such flows. And what are the key differences? The key differences basically lie in the structure of the mesh. In Paris Simulator, it's a staggered configuration. In Basilisk, it's a collocated configuration. And also in Paris Simulator, we use a fixed mesh, whereas in Basilisk, we have a dynamically adapting mesh, which according to some criteria which we can define. So moving on to the numerical development part. So one might ask the question, okay, what do we exactly mean by, if I go a slide back, what do you exactly mean by consistent methods? We shall address that question in a few slides, but let's start off with the governing equations. As you have the famous Navier-Stokes equations, you have the one fluid formulation with a variable density and viscosity. And of course, it's at the incompressible limit, so you have your divergence of u equal to 0. Over here, you have the surface tension term, which is based on the CSF model, is basically a manner in which we can map the singular surface force distribution onto its onto the volumetric equivalent. Moving on, so how do we actually track our interface? We have something called the phase characteristic function. So you have this evolution of this phase characteristic function, which is mathematically a Heaviside function. It's 0 in one fluid and 1 in the other. And following that, the material properties can be written as a linear function of these of the phase characteristic function. And so one of the key consequences is that the density field evolves according to the interface position. And now we move on to how do we actually resolve this phase characteristic function in our discrete contexts. So over here on the left, you can see you have a smooth representation of the interface with this interface demarcating the region separating the fluids. As you as you take a discrete analog of the smooth representation and you move on to a volume fraction field, which is computed, as you can see over here. And from here onwards, we can reconstruct an interface using a piecewise continuous approximation with this broken jagged line segments, as you can see over here, which is referred to as the Plick representation. So moving on, as you can see, we replaced the characteristic function with its discrete equivalent, which is the volume fraction. The volume fraction can be captured by this equation over here, and we can recast this operator into the conservative form to give us this divergence term on the right-hand side. So one might ask, okay, why do you bother keeping the divergence term? Because it's basically 0 in our incompressible limit. But as you shall see, even if the differential equation says it's 0, but it might not necessarily be the case once we discretize this in space and time, because we are basically using a direction split framework in which we integrate one direction after the other in a sequence. So it might not necessarily be 0 for each of the directions along which we are integrating. So you're basically left with something we call a directional divergence. Moving on, if I would like to highlight this equation over here, the part in the red refers to the fluxes, the part in the green refers to the compression term, as we've pointed out before. And it's just basically reiterating the same point that the directional divergence may not be 0. So we need to be careful in how we treat how we temporally integrate this equation. Moving on to how do we actually compute the fluxes. We can use either a Lagrangian framework or an Eulerian framework. In the Lagrangian framework, you basically just move the endpoints of the line segments in a Lagrangian fashion, and in the Eulerian implicit way, especially in the manner in which it manifests with the Weymouth and Yu algorithm of JCB 2010, is that you compute the mass fluxes exiting a particular control volume during, you can imagine this is a temporal integration along the x direction. And what are the key differences between these two methods? For the relevant quantity for us is, okay, we want to maintain a conservative transport, so we should ensure that the summation of the directional divergence, they come up to 0, because in the Lagrangian explicit case, they do not, as this prefactor is dependent on the substep of the advection itself. On the other hand, the Weymouth-Yu method uses a neat trick by which they can maintain the prefactor to be a constant for all the different substeps. So this ensures that you can have a fully conservative transport in 3D. So what are exactly consistent methods, as I had alluded to before? So over here I present a brief distinction. On the outset, it does not capture all of the technical subtleties involved in the discretization, but in essence, you have your mass transport over here and over here. And as you can see, in the consistent methods, you're basically discretizing the conservative form of the Navier-Stokes equation. So what does that allow us to do? It allows us to advect momentum in the same framework as that of the mass. So the advection of momentum follows the advection of mass, where the advection of mass, which is our density field, is following the geometrical volume of fluid method. On the other hand, in the non-consistent methods, what happens is, okay, you have the same equation for mass, but for momentum, you use a convective form of the Navier-Stokes, and what this does is decouples the propagation of the mass and the velocity field, which is representing the momentum. And here the velocity field can be advected using some higher order method. So basically what this allows you to decouple the transport of mass and momentum. So how do we exactly go about achieving this consistency? So one of the outcomes of the consistency is that the error in the density and momentum fields propagate at the same speed. First of all, the speed is the same, and also they are in sync, they're in the same phase. So what this allows you to do, even if the approximations for the individual fields are not quite good, but still you can maintain some issues related to stability once you are able to make them synchronous. So of course, these methods are not new. There have been major iterations throughout the last 20 years. Some of them are listed over here. So moving on, how do we exactly achieve the consistency? So this forms the central model of our numerical development part, in which we have, over here you can see this is the flux of mass, and here is the flux of momentum on the left-hand side, and this is constant proportionality, which is basically representing your momentum per unit mass. which is going to be transported. So as you can see, this simply represents the mass flux leaving the cell boundary from the right-hand side, and this is basically limited velocity, which is representing the quantity of momentum being advected. A brief example, if you can see, if you have a 3-point stencil concerning the component of momentum in which you're interested in, and this is the mass flux leaving, as shown in the boundary over here. So you can simply estimate this using you need an approximation at this center of the flux polygon. So you can use some nonlinear flux limiters in order to get an appropriate estimate. So why do we make life difficult for ourselves? Okay, already the methods themselves are difficult enough, so why do we bother making them consistent? So for this, I would need to take a brief detour. Over here, you can see.
So what are exactly consistent methods, as I had alluded to before?
So
over here, I present a brief,
falling under the influence
a brief
of gravity.
distinction. On the outset, it does not look,
we are trying to maintain approximately
it does not capture
velocity,
all
so
of
it should stay
the
more or less
technical
in the center.
subtleties
The
involved in the
important point to note
discretization,
is
but
that
in essence,
using the
you have your
methods,
mass
shall see
transport
what
over
happens.
here and over here. And as you can see, in the consistent methods, you're...
Voila, so you have these sort of exploding drops. And this is something we would address at a later point in the simulation as well, that they are what we refer to as artificial atomization. And this is primarily completely unphysical because at such a low Weber number, the Weber number is approximately 3, so you should not see any such phenomena. So why is this exactly a cause for concern? Why are we bothered about this? Because if you take a slightly more complicated simulation from Yuling and co-workers, there's nothing to single out this particular experiment, but it's just representative of the point I'm about to make, is you have a lot of droplets which are more or less poorly resolved. They don't have enough enough spatial resolution in terms of your grid size. So it's a valid question to ask, are these drops actually real? Will they skew the picture, the physical picture that we have of our atomization, and they might completely skew your understanding of the drop size distributions? Okay. Okay.
Then we can also see the animation.
Do you,
We just see the presenter screen. You know.
oh, really? No, I'm in Keynote. Yeah, I'll. Yeah. So now can you see the full screen? Ah, sorry, I haven't shared. Okay, now it works. Okay, I shall try to move this. So can I, at what point do you want me to restart? Over here or a bit further?
Where you were was fine. Where you were was fine. It's just that the animation was not visible for us.
So were you able to see the videos? And all right, so, okay, so let us recontinue. So in order to answer your question from before, why do we make our life difficult? So because you have these numerical instabilities which lead to this sort of artificial fragmentation at large density contrast, and in particular for low to moderate numerical resolution. What we are talking about is the odd, okay, unless you have a drop which is resolved by 100 points, you are in danger of seeing this sort of artificial atomization. So moving on to more serious stuff, as you can see, we need to somehow place our mass momentum consistent framework in the overall scheme of the Navier-Stokes equation. So we start off with the, we can recast the Navier-Stokes equation in a operator form, and the operator can be decomposed as you see over here in terms of the advection operator, the diffusion, the surface tension, and the volumetric force. So, and how do we exactly solve this? We use the traditional or the standard operator split framework, in which in the first box you can see we are trying to solve the coupled equations of the volume fraction field, and also the density estimate over here, which in the momentum estimate given by the U star. And the green boxes are the operators that the green boxes are highlighting are basically the coupled mass and momentum transport that we have talked about, which is basically our consistent framework. Once you obtain an estimate of the intermediate velocity field, you can then apply incompressibility, and you obtain the pressure Poisson equation. Upon solving which, you can finally project your intermediate field onto a solenoidal vector space in order to get your final velocity field, as you see over here. So this is roughly the 3 basic steps that we need to carry out, apart from doing our consistent mass and momentum transport given by the green boxes. So there's also a small issue that we need to address in the context of staggered grids. Over here you can see, because in this part of the thesis we are using Paris simulator, where the configuration is basically staggered with respect to the control volumes for mass and momentum. As you can see, a small animation. So these are the different control volumes on which your mass and your momentum are going to be centered, and the direction of the staggering depends on which component of momentum you're solving for. So this poses an additional challenge with respect to we would need to reconstruct the mass and the corresponding fluxes onto the shifted grid in order to carry out our consistent approximations. So one solution which we had developed before is something called the shifted fractions method. As you can see over here, it's if you have a centered grid on top and you have the corresponding staggered configuration, if we are looking at advection along the horizontal direction, so you would basically try to approximate. You would compute the value of these half cells in terms of the mass, and you would reconstruct a new interface once you're able to add these two shaded areas together. So this involves Plick reconstructions for each component of momentum. So it is actually adding noise at the grid scale for every time step for each of the 3 components of momentum. And on the other hand, it's this shifted field. Once you have carried out the consistent mass and momentum transport on this staggered configuration, this is actually discarded. So even though the transport is sort of conservative, but it's not fully conservative because you discard this field. We can go into a more technical specification for this thing, but I shall leave that for the supplementary material. So moving on, can we achieve both consistency and be fully conservative at the same time? There exists a solution which is known as the subgrid method, which we have developed for maybe 1.5 years during the thesis. So what you have over here is the density field is advected on a twice finer grid, and the momentum is advected on the coarser grid itself. So what this allows you to do is, as you can see over here with the shaded areas, now you have a subgrid reconstruction of your mass field, which is represented by the smaller interfacial segments over here, and the dotted lines represent the contours of the subgrid, which is coinciding with the larger centered grid. And if you need an approximation on the staggered cells, you can simply take the volume integrals of the cells over here, which would give you the staggered field. So you do not need to conduct any Plick reconstruction, and you can avoid this injection of noise at the grid scale. And when coming to the point of the fluxes, as you can see, this is the part, the shaded area in red is the part I explained to you in the previous slide. Now, if you look at the fluxes, you can also use a similar restriction operator on the fluxes in order to get the corresponding flux at the core staggered grid, all coming from the mass fluxes computed on the subgrid. So this completely solves our problem in terms of the reconstructions required at each substep for each component of momentum. So what is the novelty here? Because this idea originally came from the seminal work of Rudman in 1998. So what have we added exactly? So in the original paper of Rudman, as you can see, they were using an algebraic method, which is not at all the same thing as using a conservative geometrical mass transport scheme, as in our case. And the primary difference with the Weymouth and UA paper is that the method was originally designed for dealing with mass transport, and we were able to successfully extend it for direction split momentum transport in our consistent framework. So now we move on to the results section of this part, and it's titled The Falling Raindrop. And a question to ask is, can we actually even simulate the dynamics of something so simple such as a falling raindrop under gravitational acceleration? So first, let us look at the computational setup. As you have over here a 2D schematic, you place a drop of water in the center of the domain, and you have an inflow boundary condition from the bottom, and you have gravitational acceleration in the other direction. We try to use the velocity which is more or less, which is approximately equal to the terminal velocity, so that the drop stays more or less in the center. It's balanced. The key thing to note over here is that we are using the density and viscosity ratios of air and water at 20 degrees centigrade. So we are addressing a challenging problem in the context of large density contrasts. And the key number to note over here is the Weber number, and it's of the order of 3. So you really do not expect any sort of fragmentation phenomena to occur at this point of time. So let us start with the non-consistent method. What do we observe? As you saw in the previous slides, so you get something which we term as artificial atomization. The drop completely fragments into a million smaller particles, and there is very little we can do to distinguish between the physical drops and the unphysical drops, as we can say. So, and this is at a more or less low resolution of 16 points across the diameter. So what causes this instability exactly? As I alluded to before, when you use a non-consistent framework, you are decoupling the propagation of the error fields corresponding to the momentum and the mass. So what happens is, due to this decoupling and due to the large density contrast, these small numerical instabilities get amplified very quickly. What that results in is, over here you have the pressure plot corresponding to the initial instant of the simulation. The velocity field is something of a dipolar velocity field corresponding to a potential solution, with the stagnation points at the front and the back of the droplet. In this case, you can see you have a massive pressure spike in terms of the pressure gradient. And why is this occurring? You obtain a mixing of the gas velocity with the liquid density, which is basically completely skewing your gradient of the pressure. And due to these huge pressure spikes, you are forcibly deforming the shape of the interface on very fast timescales. So this is basically what you can understand in terms of the mechanism of the instability. So do we perform any better with our consistent schemes? Yes, we do actually. As you can see, in both cases, using the subgrid method or the shifted fractions method, we are able to completely stabilize this raindrop in terms of, at this point of time, I cannot comment on the the fidelity of the model with respect to an actual falling droplet, but at least we are able to stabilize the situation and prevent any artificial fragmentation. So now revisiting the pressure spikes, comparing the consistent and the non-consistent framework, as you can see for the same resolution, now over here you do not observe any more pressure spikes, and the only jump in pressure you see over here is the Laplace pressure across the interface. And an additional point of information is also, you can compare the droplet kinetic energy as it evolves in time. Over the red curve corresponds to the consistent method, the green curve corresponds, of course, to the non-consistent method, and you can see this. There's orders of magnitude of separation in the kinetic energy, as you can see on the log scale, and these spikes of kinetic energy correspond to these massively deformed interfacial shapes as well. And one important point to keep in mind is that we're looking at small timescales relatively, which is given by TC over here, which is the timescale corresponding to capillary oscillation of the second mode. So can we obtain converged results in our case? So for the convergence study, we use a slightly relaxed inflow velocity corresponding to 5 meters per second, so that we can actually simulate the dynamics of the initial physically consistent acceleration before it reaches the statistically stationary state. Over here on the graph on the top left, you can see the kinetic energy. It gets more and more smoother, and you reduce the amount of spurious kinetic energy as you increase resolution. And the kinetic energy is with respect to the motion of the center of the mass. So this is in the frame of the droplet itself. And you can see for as you move on to plots B, C, and D, these are basically the moment of inertia in the 3 different directions. And you see a similar, more or less convergent behavior as you keep on increasing resolution. And this moment of inertia is acting as some sort of average indicator of the droplet shape at any particular instant of time. So this is carried out with our subgrid method, as I discussed before. And finally, if you also look at the droplet, the velocity of the droplet center of mass versus time, as you keep increasing the numerical resolution, you do have seemingly convergent behavior. It's not quite there yet, as you can observe from the inset the fit of the acceleration versus time as you keep on increasing resolution. The error bars are the difference in the acceleration estimates are decreasing, but no apparent order is visible right now, and we get an acceleration estimate for about 4.8 meters per second square. So we are able to successfully capture the initial phase of the droplet acceleration before it reaches a statistically stationary state. So with that, I shall conclude the part A, and we shall move on to part B. So the part B, in part B, we are basically using our numerical methods in a different platform, which is Basilisk, in order to answer some very pertinent questions in terms of the physics of fragmentation. So let's start off by what do we exactly mean by fragmentation or atomization. So fragmentation is the process by which you have an initial liquid structure which is breaking down successively into smaller and smaller sizes via passing through several different topological structures. Let us demonstrate a few examples. As you can see over here, this is the classic disintegration of liquid cylinders with these popular experiments. As you can see over here, you have simply a cylindrical liquid structure which is disintegrating due to the destabilization of the capillary forces, and finally you get a collection of drops of different sizes. So this is quite a simple example. If you move on to a slightly more complex example in which you have liquids impacting a solid obstacle, on the top side you can see a drop impacting a solid obstacle and the sheet expanding and the sheet of liquid expanding. And what happens is during this radial expansion is that the edges of the sheet face a capillary retraction. So what happens is there is accumulation of mass at the edges, which finally form these sort of rims. And the rims over here, they themselves destabilize to form a collection of drops. And in this case, you have in the experiment on the bottom, you have a steady mass flux instead of a single drop. But you can see more or less similar qualitative features, even though the mechanisms are not exactly the same. And finally, moving on to a more peculiar case, over here you see a liquid sheet, but it's not, you do not form these ligaments and these drops from the edges. Instead, they're formed from the body of the sheet itself because of the presence of these holes or these perforations. And upon the expansion of these perforations, you have these similar rim-like structures, which again decompose to form a set of drops of different sizes. So what the common takeaway from all of these different examples is that the ligaments constitute the penultimate stage in fragmentation. And how do they exactly govern the polydispersity in the drop sizes? As you can see, that it is very difficult to predict what is this drop of the size going to be exactly by looking at a ligament. So do we have any good manner to explain that? So we fall upon this popular framework which is known as the corrugation coalescence mechanism, first proposed by Villermo and co-workers in the 2004 paper. So basically the message is that you have these corrugations in the initial shape of the ligament, which determine the subsequent nonlinear liquid rearrangements within the body. And once the ligament breaks up, you can reach larger drop sizes due to the subsequent coalescences. And you can use this quantity called n, which is sort of like a inverse of a variance, in order to characterize the degree of smoothness or corrugation of the initial ligament structure. And one qualitative prediction of this framework is that for n tending to infinity, you would have a monodisperse drop size distribution. For n closer to 1, you would get, which represents more corrugated ligaments, you would get a more polydisperse collection of drops. So moving on to a more quantitative prediction of this model is that, as you can see over here in this figure, and the commonly used probability density functions are given over here, is that they give you different results in terms of when you're looking at the statistics of drop sizes and how they're distributed. So you can see a clear distinction between the gamma, the log normal, and the Poisson, especially for at the limit of larger sizes, because at the leading order terms for the log normal is going to be exponential of minus log x. In the leading term for gamma is going to be exponential of minus x. And I think I forgot to put the Poisson over here, but it's a Poisson in volume, so it's going to be exponential of minus x cube. So as you can see, the slopes correspond accordingly at the limit of the large sizes. So do we accept this picture? Not really. So one of the ways in which we set out to answer some of the questions related to the impact of the corrugations is, can we actually verify if the corrugation, can we actually quantify and also verify at the same time if the corrugations do lead to polydispersed drop sizes? Basically, we decided upon this roadmap in which you first design a single corrugated ligament in which we can precisely control the statistical properties of the shape. So this is going to follow completely deterministic dynamics, and you're going to get a deterministic set of drops. Now stochasticity is going to be added to the mix by creating an ensemble of such random but unique corrugated surfaces, where each realization of the ensemble is going to be random, but it's going to be random but unique at the same time. So from this, we are going to generate droplet ensembles. So in the first part, you have one single ligament. In the second part, we are going to simulate thousands of such ligaments to get thousands of such drops. And this is what we basically term as a Monte Carlo approach to DNS. And finally, once we have a sufficient amount of drops, we can actually carry out some statistics based on the drop size and other quantities of interest. And we can also map out the influence of the initial conditions surrounding the configuration of the ligament and its impact on the subsequent PDF that we shall obtain. So which numerical platform do we use in this case? We revert to Basilisk, primarily due to the fact that you can have an adaptive mesh resolution depending on if you try to do this with an equivalent. If you're looking at slender structures and you use a regular Cartesian grid, it's gonna be way more computationally expensive in order to resolve all of the fine scale structures. You can see an example from a simulation I've done myself. You can have a much more refined mesh near the regions of interest, in which would be really more expensive with a standard mesh, a regular mesh. So how do we create a corrugated surface in the first place? So it's very simple. We use a state-of-the-art white noise generator, and we pass it through a low-pass filter, keeping the first NC longest discrete wavelengths. Over here, you can see the green curve. The green curve represents the initial signal, and the bolder black curve is the filtered signal. So this is going to be our final profile for the ligament shape. Moving on, how do we characterize this with our set of non-dimensional groups? First of all, you see the computational setup over here, in which basically we need to go for slender structures, so large aspect ratios. So you have the mean radius is R, and you have and the length of the ligament will be L, and we are looking at periodic ligaments so as to avoid the end effects. So one of the key points is that, again, we are talking about air-water density and viscosity ratios. You have the Ohnesorger number, which basically sets the length scale when you're talking about air-water systems. You have a normalized parameter, which is representing the strength of your initial corrugations based on the variance of the initial white noise signal. And you have the aspect ratio. You have a non-dimensionalized wave number, and you also have your time scales normalized by the capillary time scale. So one question to ask is, okay, do you go for axisymmetric or full 3D? So I've done a simple comparison over here. You can see the temporal evolution of the axisymmetric simulations and the full 3D simulations on the top and the bottom rows respectively. And if you can focus on any one particular row corresponding to the same instant of time, you can see there's not much difference in terms of the drop shapes and sizes that we are interested in primarily. And we can do this with the axisymmetric setup by saving of time by a factor of 20 in terms of computational expense. So obviously, we choose to go for the axisymmetric setup because we plan to do thousands of such simulations and not just one sole ligament. So how do we generate a large number of drops? We just vary the seed of the random number generator, and we get different ligament shapes which correspond to the exact same statistical description of the shape. So each realization of the ensemble is characterized by this by phi, which includes all your initial conditions as we described before, and you also need to add a temporal component to this number in order to completely characterize your droplet ensemble, because as you have coalescences progressing in time, the distributions do have a temporal variance inbuilt within them. Moving on to the first key result, we have to focus our attention onto milliliter scale ligaments, and the milliliter scale is represented by the honest organ number over here, which is 10 power minus 2. In the case of air-water systems, this corresponds to millimeter. And one of the first results is regarding the diameter distribution at a particular time that we chose, which is sufficiently long enough. So it's t equal to 30. There are two key points that I can talk about here. The first key point is that the Gaussian, the log normal, and the gamma, out of all of these three different plots, the Gaussian does seem to be the best representation for this for the drop size statistics we have over here. The diameters are normalized with respect to the mean, and the second key thing in the that we can see in the inset is that the error on
that
the
you can have an adaptive
scale
measure
as 1 by
solution
under root
depending
n
on
as we keep increasing the sample size. So we have
if you try to do this with an equivalent, if you are looking at slender structures and you use a regular Cartesian grid, it's going to be
that there are no
it's going to be way
or
more
hidden
computationally
correlations
expensive
between
in
the
order to
different
resolve all
realizations
of the
in our
fine
ensemble.
scale structures. You can see an
So
example from a simulation I've done myself.
What are the influence of the initial conditions with respect to what do they
have
actually change in our drop
much
size
more refined mesh near the regions
over
of
here,
interest.
I have two different
which,
ligaments corresponding to
which would be really more expensive
they are
with a standard
characterized by
mesh,
the same set of
a regular mesh.
numbers, but the only thing
So
that
how do we
differs
create a
is
corrugated
the
surface
initial
in the first
corrugation
place?
strength,
So
which
it's
is
very
0.4 in this case, 1.6
simple. We use the
in the
state
other
of
case,
the
and you can clearly make out which amongst these two ligaments are the more perturbed. And if you would like to, if I can show you a small video of how they evolve in time. So some of the interesting things will appear just near the end, and I can also freeze this frame and take a closer look. Over here you can see the clear distinction in the trajectories that these ligaments have followed in terms of their destabilization, and mainly with respect to the presence of these extremely small drops, as you can see at several locations for in the case of the weakly perturbed ligaments. And so what kind of impact does this have on our drop size distribution is, for the case of the strongly perturbed ligaments, as you can see, it did not have that much variation in the drop size, so everything's more or less symmetrically distributed around a mean. And here you are tracking the temporal component as well. Time starts from t equal to n on top and going down till t equal to 30. As you can see, there's also a linear trend in the evolution of the mean of this symmetrical Gaussian-like distribution. So this is for the strongly perturbed ligaments. Now, what happens if in the case where the initial corrugations were much weaker and you had these presence of these extremely small drops? So now they're going to completely change the nature of your distribution itself. Doesn't matter at what instant of time you look, you always have these peaks near the small end of the spectrum, which correspond to your tiny drop sizes. And as time goes on, you see these small drops also merging with the largest drops, which are just on either side of it. And so basically, it's a transfer of these drops onto the right-hand side of the distribution, which is slowly making this plateau region at the end. So if I can summarize the last two plots which you've seen before by juxtaposing them one on top of the other. Over here you see the temporal variation on the x-axis, and you rescale the diameter by the initial width of the ligament W. And at long times you do not see any significant difference between the means, which are denoted by these dashed lines. But again, the nature of the varied distribution is completely different. It changes from a bimodal to a unimodal nature. And also a final point of reference is that, okay, sometimes you can also use sometimes you can compute an equivalent diameter by considering the volume contained under one wavelength, which corresponds to the optimal wavelength of the Rayleigh-Plateau instability, to just get an idea of the size of the drops you form. So it's in both cases, for the weakly perturbed as well as the strongly perturbed ligaments, we do not observe any peaks corresponding to that particular equivalent diameter of the Rayleigh plateau. So with that, I shall finally move on to the conclusions and perspectives. In part A of the thesis in the numerical development, we have carried out a thorough exploration of the numerical instabilities which occur in the context of large density contrast coupled with poor spatial resolution, and especially in the context of the raindrop simulations. And then in order to address those issues, we have developed mass momentum consistent methods in which we are able to successfully stabilize some even suppress some of these instabilities, as it was demonstrated in the case of the falling raindrop. And on top, we can even say that we have more or less converged results for at least the initial part of the physically consistent acceleration towards the statistically stationary state. And in terms of the physics of fragmentation part, first of all, we were able to design precisely controlled and reproducible numerical experiments in the context of whenever you're trying to look at destabilization of ligaments from an experimental point of view, it's very difficult to obtain the precise ligament. So the numerical aspect does allow us to make it reproducible. And on the other hand, we've obtained converged distributions with a sufficiently large sample size of the diameter distributions, and we also obtain a scaling of 1/√n for the sample size, which again signifies that we do not have any unforeseen correlations within the different realizations of our ensemble. And finally, we do observe that the drop distribution completely changes in nature from a unimodal to a bimodal characteristic when you simply vary the initial strength of the corrugations, which is more or less to be expected in terms of the qualitative nature of the corrugation coalescence mechanism. And finally, in terms of the perspectives, we would like to develop a high fidelity model of a raindrop starting from the initial acceleration to the final steady state. We can also use a more accurate curvature computation method. We can see if all of the methods, the consistent and the non-consistent, converge to the same thing at higher resolutions. And we would also like to compare with Basilisk the results we have with Paris Simulator. And finally, in the physics of fragmentation, we would like to further explore different points in the parameter space. We would like to include the effects of shear and higher Weber numbers. We would also like to find some sort of scaling of d by w as a function of the parameter space. And finally, we would like a theoretical explanation of the results we have found so far using Gaussian random process theory. So with that, I shall end my presentation. So thank you very much for your attention, and I'm open for any questions and feedback. So.
Okay, thank you very much. We'll move to questions.
Yes.
We'll wait for people to move first. So we will start with the reviewers of your PhD manuscript. So traditionally we start with the
sorry,
with
well,
the furthest.
1 second, Stefan. We can.